an hour, so why don't we get started? We're very happy to have Nick Sheridan from Edinburgh University speaking about the Gamma and SYZ conjecture.
Thanks very much. So I'm screen sharing. Can you see?
Yes, yeah, I can see the OneNote.
Okay, all right. Oh, okay. Thanks very much for inviting me to give a talk. So I'm going to talk about this joint work with Mohammed Abu Zaid, Sheel Ganatra, and Hiroshi Iritani on the Gamma and Strominger-Yau-Zaslow conjectures. And in this introductory part of the talk, I'm going to focus on what is the Gamma conjecture, the Gamma conjectures in the Calabi-Yau case. All right, and I hope I won't have any technical difficulties. Like I was saying just before, my usual laptop that sometimes refuses to charge, now always refuses to charge. So now I'm on the laptop where sometimes the screen turns bright purple, but it's not bright purple at the moment. And I have a backup in case that happens, but you know, we'll hope for the best. All right. So I'm going to start by introducing the notion of a complex variation of Hodge structures over a base M. So here M is a complex manifold, and complex variation of Hodge structures consists of a holomorphic vector bundle V together with a filtration F and a flat connection nabla. And these are required to satisfy Griffith's transversality. And that's a condition that means the connection doesn't preserve the filtration, but it only hurts it by 1. So it sends FP into FP minus 1, just the next level up of the filtration. All right, and I also want to introduce the notion of a polarization of one of these structures. So that's a pairing satisfying these conditions here. But I don't know, like I don't want you to get too wrapped up in thinking about these conditions. So you know, I've put them on the screen, but now I'm going to move them away. All right, I'm going to move them off to the side here so I can write there. Where you go, where you go. All right, good enough. All right, so the classic example of one of these objects is when we've got a family of smooth, compact Calabi-Yau-Kähler manifolds, Y. Then we've got such a complex variation of Hodge structures, and it's the vector bundle V has fiber. The M is just cohomology of the fiber of this family over the point M. The filtration we put is a version of what's called the Hodge filtration. looks like that. So if you drew the Hodge diamond of your complex manifold Y, then this would be sort of the smallest bit of the filtration, and this would be the next smallest, and so on. It's sort of, sorry, running around this way. This would be the smallest. This would be the second smallest, and so on. So you kind of slightly changing the usual Hodge filtration so that it's vertical in the Hodge diamond. And there's this connection on this called the Gauss-Manion connection. And that just comes from, I mean, it's there naturally because a family of smooth, well, you know, our family Y is locally trivial as just as a family of smooth manifolds, and this so this cohomology of the fibers varies locally trivially. And this has a polarization which looks like this. Okay, so associated to our family Y, we've got a complex variation of Hodge structures over the same base, and it looks like this. All right. So we're going to have another construction of a complex variation of Hodge structures, which this time is associated to a symplectic manifold. We've got a smooth, compact Calabi-Yau variety together with a Kähler-form omega. And that gives rise to a complex variation of Hodge structures over a punctured disk delta star. See the star. And we're actually going to use the parameter capital T, which is inverse of little t, on this punctured disk. It'll make the rest of the talk work. Okay, so that's the base of our family. The fiber is just the same as, or maybe I should fiber T. It's similar to the complex variation of Hodge structures we defined before. The fiber is the cohomology of X. And the filtration is different from the one before. It's the one I drew by mistake. It's just the filtration by degrees. So if we drew the Hodge diamond of X, this time the smallest bit of the filtration looks like this, the next smallest looks like this, and so on. So it's rotated, or it's reflected in a 45-degree line from the filtration that we saw on the complex side. Okay. The connection is called the Dubrovin-Giventhal connection. And with respect to the canonical trivialization that's sort of given to us from the way we've defined this vector bundle, the connection matrix is given by quantum cut product with the cohomology class of the Kähler form omega. All right, and but before I say what that is, just to establish conventions, let me say what the polarization of this is. I hope I am getting my conventions with the powers of I correct. But it's again a version of the integrate pairing. All right, and just so there's no confusion, I'm going to say what this definition of this quantum cut product is. I like to think of it in terms of cycles, Poincare dual to cohomology classes. And so we sum over holomorphic maps from a sphere with 3 marked points, 2 points constrained to lie on the cycles alpha and beta, and we look at the cycle swept out by the remaining point, and we take the sum over all of these weighted by t to the minus omega of u. All right. So this also defines a complex variation of Hodge structures. And mirror symmetry matches up these two different constructions of complex variations of Hodge structures. So we suppose that we've got a B side, Y is a family of Calabi-Yau varieties over a punctured disk, and the puncture corresponds to a large complex structure limit, sort of a maximal degeneration of the variety. On the mirror side, we've got some family of symplectic Calabi-Yaus over the same base, which you can think of. I mean, we've only put one Kähler form, but you can think of it as being a family given by multiples of that Kähler form. And here, as t goes to 0, you have what's called the large volume limit. So the Kähler form gets very, very large. And if these two are mirror, then you expect to have an isomorphism of complex variations of Hodge structures over the punctured disk, and the map between the two punctured disks on the two sides of mirror symmetry is called the mirror map. Okay, so this version of mirror symmetry is enough for you to extract predictions about genus 0 Gromov-Witten invariants. For example, the classic predictions of Candela, Stella Ossa, Green, and Parks about genus 0 Gromov-Witten invariants of the quintic threefold, they can be deduced from an isomorphism of complex variations of Hodge structures like this. Okay, so that seems like, this is maybe all that we want. Is if we can study Gromov-Witten invariants with them, maybe we're happy. But the gamma conjectures are about refining this this version of mirror symmetry to get an isomorphism of Z or Q variations of Hodge structures. So let me tell you what those are. So a Z variation of Hodge structures is defined to be a complex variation of Hodge, or I define it to be a complex variation of Hodge structures together with a lattice of flat sections. So this means so a local system of, well, a Z to the N local system, sorry. So that when you tensor with the complex numbers, you get the C to the N local system of flat sections of your complex variations of Hodge, variation of Hodge structures. And there's an extra condition that this should make one level of the Hodge filtration complementary to the opposite level after you complex conjugate using the complex conjugation induced by this choice of lattice. And if you want to talk about polarizations, then there's an additional positivity condition about this pairing. All right, so the reason—
Can I ask a question?
Yep.
Is it not assumed that the two flat structures are the same? Like the connection you get from the lattice and the connection you're given?
Yes. I mean this VZ here is defined to be
flat sections. I'm sorry. I'm stupid. Yeah. Sorry.
No, thank you. Thanks for the question. All right. So very briefly, why do we care about this refinement of this complex variation of Hodge structures version of mirror symmetry? Why is a Z variation of Hodge structures better than a complex variation of Hodge structures? It contains information about periods. Maybe I should actually have said my first example in order to explain that. So in the case of the B model variation of Hodge structures, there's a very natural lattice of flat sections, which is given by the integral cohomology of the fiber. So, if you have this extra data, then you can work out, extract from it periods of your variety, which means integrals of the holomorphic differential forms over topological cycles. And these are very interesting to study in arithmetic geometry and so on. So there are reasons why we care about this more refined structure. All right, so we have this, this very natural lattice on the B side. So actually, we want to change it slightly. So I'm gonna, but We want to multiply it by some powers of 2 pi I, but don't worry too much about that. Just think about it as recording the data of these, the integral cohomology of the fibers. So now you might think, okay, what's going to correspond to that inside the A variation of Hodge structures? Well, you might think that you just take the integral cohomology of X sitting inside your A variation of Hodge structures. But that's not right, because these sections are not even flat with respect to the connection. Remember, with respect to the natural trivialization of our A variation of Hodge structures, we had a non-trivial connection matrix. Okay. So what you can do is look at sorry, I'm gonna twist by some powers of 2 pi again, but I don't want you to think too hard about that. So instead of just saying these integral cohomology classes, which don't define flat sections, we can say flat sections with a certain asymptotic behavior as t goes to infinity. So so this t to the omega is by definition the exponential of log t times the cohomology class defined by omega. And if we cup with this, then if you look at the connection matrix of the de Broglie-Giventhal connection, you can see that flat sections have to have this kind of asymptotic behavior as t goes to infinity. All right, so now we've defined something here, which is a perfectly valid lattice of flat sections inside our complex variation of Hodge structures. But this is the wrong answer for mirror symmetry. If you try to put this, if you look at this Z variation of Hodge structures, then you will not get an isomorphism of Z variation of Hodge structures in mirror symmetry. Instead, what you need to do is cup with something extra, which is called the gamma hat class of X. So I'm going to reveal this now. Hopefully this will work. Come on, no, don't do it. All right. Come on. Well, this is unfortunate. Come on, laptop, you can do it. Okay, all right, I'm not going to risk trying to drag it further up. This extra thing that we need to cup by, this gamma hat class, is some characteristic class of X. Right, so it lives in cohomology of X with complex coefficients. So it's not changing this asymptotic behavior of T that we put in there. So one way of writing it as the product of the Euler gamma function of 1 plus delta I, where delta I are the Chern roots of the tangent bundle. You can also write that in this form, and where this zeta of k is the Riemann zeta function, and it might help us even more to see it expanded out according to the cohomological degree of the terms. Okay, so we'll call this, so this is gamma hat 0, the part in cohomological degree 0. This is gamma hat 2, the part in cohomological degree 4. This is gamma hat 3, the part in cohomological degree 6, and so on. So you can see that zeta of 2 shows up in the second bit, and zeta of 3 shows up in the third bit, and so on. All right, so the gamma conjectures, which build on work of many people, say that mirror symmetry should work as an isomorphism of few variations of Hodge structures if we use this gamma integral structure that we just defined in VA of X. And then a related conjecture says that if we've got a Lagrangian in Y mirror to some complex of coherent sheaves in X, then under this isomorphism, the class Poincare dual to this Lagrangian gets sent to the class the flat section asymptotic to this gamma hat cup T to the omega cup the Chern character of this complex of coherent sheaves, E. Some other things that match up are the holomorphic volume form and the class of the identity in the A variation of Hodge structures. Which means that we can pair this LT with this omega T, and we should get the same thing as if we pair this this flat section up here with 1. So the period integral of our holomorphic volume form over a Lagrangian its asymptotic should be given by this integral over x, modulo negative powers of the variable capital T. Okay, so that is the end of the introductory part of my talk. And yeah, so I guess we can have discussion now and questions.
Are there any questions for Nick that want to be recorded?
Why is the first part of the conjecture stated in terms of Q variations instead of Z variations?
So to get a statement that has a chance of being true with Z variations, you should replace the integral cohomology. You should replace what I wrote with the image of the Chern character from the topological K theory of the variety, and then I believe there's a I think there's not known to be counterexamples to that conjecture, but it's maybe a more it's a more daring conjecture than the one with Q variations.
Thank you.
I have another question.
Yeah.
Why does the Lagrangian appear on the B side? I mean, isn't that kind of strange?
Yeah, it's bizarre. Yeah. Like, so the first, I mean, part 1 of the conjecture looked kind of okay, but part 2 of the conjecture, we see that the integral structure, we're looking at, you know, a complex variety. We're looking at the B variation of Hodge structures, but the integral cycle is coming from a Lagrangian, which is an A brane. And similarly, on the A variation of Hodge structures, we're getting a flat section which comes from E, which is a B brane. So yeah, it's pretty weird.
Okay.
But that's what the conjecture says.
Maybe I'll pause the recording if people want to ask any informal questions.
Sure. All right. Okay, so let me just say one final thing, which is what I said in response to Nicholas's question, that, you know, there is some hope. Well, we know, following work of several groups of people, we understand well now that when homological mirror symmetry is true, then I mean, in some certain settings that I'm not writing the precise conditions here, that this implies that we have this isomorphism of complex variations of Hodge structures. And it would be nice to upgrade this to, it would be nice if we could replace this C with a Z or a Q. And so since we already have this isomorphism of complex variations of Hodge structures, as I said in response to Nicholas's question, to upgrade that, it suffices to match the lattices of flat sections on the two sides in the limit t goes to infinity. And that is why in this formula here, I was perfectly happy to write a formula which is only asymptotic in T, because that would be good enough to upgrade this result. All right, so this formula is actually the one that we are going to focus on. So this is what I'm going to call gamma conjecture 2, is this formula. So period integral on one side and some asymptotic formula for it in terms of an integral over the symplectic manifold on the other side. And our main theorem is that this formula that I just put a square around holds if X and Y are Batirev mirrors, so mirror Calabi-Yau hypersurfaces in Farnow-toric varieties, and E, the complex of coherent sheaves, is a line bundle restricted from the ambient toric variety. So this result is not, well, the proof of this result is, sorry, it's not the first proof of this result. There's a proof due to Iritani from before. The point of what we've done is that we give a new proof of it based on the SYZ conjecture, which gives some additional geometric insight into why it holds, and gives a prospect of generalizing it beyond to cases where it hasn't been proved yet. All right, so I'm going to focus on a specific case for simplicity. I'm going to focus on the case that E is the structure sheaf. So the Chern character is just the identity. So then this formula that I wrote here reduces to this. So modulo negative powers of t this period integral is equal to the integral over x of this gamma hat class cupped with t to the omega. Okay, so that's just what happens in here if the Chern character here is just equal to the identity. And so we can expand this out according to the cohomological degree of the pieces that we're matching up. and we get a sum that looks like this. We get a sum over the degree 2i part of the gamma hat class with the degree 2n minus 2i part of t to the omega, which looks like this, just by the formula for the exponential. All right, so I'm going to try to explain what the proof looks like in this case. So like I said, it's based on the SYZ conjecture, where we've got torus vibrations over a common base with a singular locus in codimension 2. So locally, the symplectic torus vibration looks like a moment map for a Hamiltonian torus action. And the algebraic, on the algebraic side, at torus vibration looks like the map from C star to the n to R to the n that takes log t of the modulus of the coordinates. So that's sort of the 0th order bit, and then we need to correct by holomorphic disks emanating from the singular locus, weighted by t to the minus area. Okay. So to continue, what the local model looks like, the holomorphic volume form looks locally like d log z1 wedge blah 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 wedge d log zn, and the Lagrangian cycle, which is mirror to the structure sheaf, looks like the positive real locus sitting inside C star to the n. So that means that that our period integral, the left-hand side of this equation we're interested in up here, looks like the integral, it looks like log t to the n times the integral of just the affine volume form over B. All right, so that's the sort of uncorrected answer. And by the Dustermaat-Heckmann theorem, this affine volume of the base is equal to the symplectic volume of the total space. And this is exactly the I equals 0 term of our equation up here. So the I equals 0 term of this sum. And the other terms in that sum come from the corrections. And since we're working modulo negative powers of t, we actually don't get any contributions other than from the constant disks on the singular locus. And that's why the computation of the asymptotic behavior is local in B. And it also turns out that this gamma hat I, the ith term in this sum, arises from the codimension I part of the singular locus, B sing. All right, so here's what it looks like in the case that X is a K3 surface. So here, B is a two-sphere. The singular locus consists of 24 points. And all right, so here's a chain of equations connecting the two sides of our formula in the opposite order from which I wrote it up here, but it's the same formula that we're trying to understand. So we start with the integral on the symplectic manifold first. So expand out t to the omega. So that's x of log t times omega. So that looks like this. Of course, there are no higher terms because it's a cohomology is in degrees less than or equal to 4. And the part of the gamma hat term is 1 minus 24 zeta of 2 times, well, Poincare dual of a point. So when we integrate that out, we get this term log t squared times the symplectic volume minus 24 zeta of 2. And as we just saw, this leading term by the Heckman theorem is equal to the affine volume of the base B. And these two terms combine to give the asymptotics of this period integral. The first term is the leading term that we just computed up above. And the zeta of 2 term is the contribution arising from constant disks on the singular locus, on B sing. So each of the 24 singular fibers in our SYZ fibration contribute minus zeta of 2 to the asymptotics of this period integral. Okay, so that's the case of K3 surfaces. So what about a Calabi-Yau threefold? So in this case, the base is going to be a 3-sphere. The singular locus, roughly speaking, is some kind of trivalent graph inside the 3-sphere. So what does this integral over our symplectic manifold look like? Well, again, we expand it out and we get a leading term that's the symplectic volume as before. We get a the next term is in log t, and that's zeta of 2 times the integral of the second Chern class of the tangent bundle coupled with omega. And the third term is just minus zeta of 3 times Euler characteristic of x, which I guess maybe I should have written as integral over x of C3. All right, so now we want to, as before, interpret this in terms of the affine geometry of the base. The leading term, as we've seen, is the affine volume. You can interpret this C2 coupled with omega as the affine length of the singular locus. And then you can interpret this Euler characteristic as a signed count of the vertices of this singular locus. So there are two kinds of vertices, one that contributes +1 and one that contributes -1. But you add those up over this trivalent graph and you get the Euler characteristic. And finally, we will see that this matches up with the period integral. We've already seen the leading behavior. Then we've got the contribution coming from constant disks on the edges of the singular locus. And then we've got the contribution coming from constant disks at the vertices of the singular locus. And those equal the period integral. So you can see how I mean, we wrote out a complete proof in the case of these Batirev mirrors, but you can well believe that the approach here would work much more generally for Calabi-Yau threefolds that satisfy SYZ mirror symmetry. Okay, so now's the fun bit of the talk, which you can understand even if you're lost with the rest of it. It's about how we actually do these local computations and where these strange Riemann zeta values come from. So it's all about, sorry, is there a question?
Did you actually explain about, maybe I missed, did you actually explain why this period integral over the Lagrangian is this number, I missed that part completely.
Like this step here?
Yeah, the last equality, did you?
No, that's what I'm about to explain. That's
Okay.
That's the content of the remainder of my talk.
Sure.
Okay, so it's based on this Maslov dequantization, which is a fancy name. Oh, I was supposed to erase that. No. Oh well. Forget about this bit here. for the moment. As t goes to infinity, log base t of t to the x plus t to the y converges to the max of x and y. And this is fundamentally how we interpolate between algebraic geometry and tropical geometry. So as an example of that, we consider this polynomial, t-dependent polynomial in A, 1 plus A plus t inverse A squared. This Maslov dequantization says that the limit of the log of the polynomial applied to t to the x is equal to something piecewise linear, the max of 0, x, and 2x minus 1. So here's a picture of the graph of the log of a polynomial and the piecewise linear thing. So we're going to try to use this to compute integrals. So we, as a first step, try to compute the area under these graphs. So the integral of the left-hand side is approximately equal to the right-hand side. But there is also a sub-leading term, modulo t to the minus epsilon, which comes from these areas where the bends happen. So there's a little bit of area at the bend where the red line is forced to move away from the blue line. And you can work out that that area is zeta of 2 over log t. So since we've got two bends here, we get a contribution of 2 zeta of 2 over log t. All right, and the explanation for why the subleading asymptotics come from the bends is sort of here, that if x and y are separated by epsilon, then this is an approximation that works modulo t to the minus epsilon. But if x and y are equal, then there is then it is not as good an approximation. All right. So I'm going to go on to an example of a polynomial in 2 variables. So here we've got a t-dependent polynomial in A and B. Looks like this, -1 plus t inverse A plus B plus 1 over AB. And so we do the same thing as before. Here on the left, we've got a picture of the domains of linearity of our piecewise linear function. We've got 0 in the central triangle, x minus 1, y minus 1, minus x minus y minus 1. And on the right is a 3-dimensional picture where the blue is the piecewise linear, the graph of the piecewise linear function. The red is the log of a polynomial. And if we try to estimate the integral of these 2 functions over some bounded domain U, as I've drawn, then once again we get some subleading asymptotics. We get zeta of 2 over log t multiplied by the total length of this triangle with 3 legs coming off it that sits inside the green domain. And then we get 3 times zeta of 3 over log t squared. And that 3 comes from the fact that there are 3 vertices here. So we get a zeta of 3 from each vertex. And that's everything. So how does this work, for example, for the focus-focus singularity? So that's given by the equation xy equals 1 plus z, sitting inside c squared times c star. We've got a formula for the holomorphic volume form here. And our Lagrangian LT is going to be the positive real locus. So if we introduce the parameters A, B, and C, which are log of the modulus of these variables, X, Y, and Z, then the restriction of our holomorphic volume form to LT is equal to dc wedge dB, which is equal to minus dc wedge dA. And now I want you to, so now we're going to try to understand what the contribution of a focus-focus singularity in our SYZ fibration is to this period integral. So imagine that you're cutting up the base of your SYZ fibration by sort of, you know, into polygons. Then over on this side where A is big, A, C are good coordinates on, you know, linear coordinates on the base of our SYZ fibration. Over here where A is small and B is big, B and C are good coordinates. So since we want to cut things up using the into polygons in the base of our SYZ fibration, over here where A and C are coordinates, we want to define a region by linear inequalities in A and C. So we say C is between minus K and K, so that's sort of the top and the bottom bit of our polygon. And A is less than or equal to K, that's the right-hand side. Over here, A is not a good coordinate, so instead we use B, and we say this left-hand side of our polygon is given by B is less than or equal to K. And since B is equal to log of 1 plus e to the c minus a, this exactly gives this kind of difference between the polygon that you might imagine you would get and the contribution to the period integral that you actually get. So we're missing zeta of 2 from our period integral based on what we might expect based on, you know, just computing the area of the base. And so that's the explanation of how the things I did on the previous 2 slides give rise to these contributions to actual period integrals. Okay, I think I'll stop there.
Great, thanks so much for the great talk. Let's give the speaker a round of applause.
Thank you.
So are there any questions for Nick?
So what about the, I mean, the gamma is not quite a square root of the Todd, right? It's like gamma times gamma bar or something like that.
Something like
so
that, yeah.
Is there another integral structure coming from gamma bar, or how does that work?
I don't think I have a good answer. I mean, when I read Iritani's papers, I certainly see gamma bar appearing. But I don't know if the right way to think of it is as a different integral structure with different properties. Sorry.
So maybe if I maybe just indulge everybody else. So I mean, if I think of the Todd class as a correction that I need to do to compare the volume of a polytope with the number of lattice points in it, the gamma class the way that you present it is sort of similar. It's some sort of correction that you need in order to compare some sort of you know, volume computation with integral of some polynomial. Isn't that right?
I don't know the relationship between the Todd class and volume and number of lattice points in a polytope, but I don't. I mean, do you want to explain it and I'll learn something, or I don't know the analogy. Sorry.
Yeah. So if you think of the Euler characteristic, for example, of say the hyperplane class is given by Riemann Roch, and so that's you know, say for has a basis given by lattice points. So you see you get some relation between the number of lattice points and the volume with corrections coming from the Todd. And
I see.
I had never seen this idea of gamma class arising from the corrections that you need to, you know, coming from the corners of something, which is basically what you're saying. Is that new from your work?
Yeah. Well, I mean, you can find. So you can find the result that like pi squared over 6 shows up in the area of a tropical amoeba of a curve in the literature by Passer, Mikhail Passer, but yeah, in terms of the gamma hat class sort of showing up in this way, relating to the singularities of sort of the bend locus, the higher dimensional tropical polynomials and so on, I think it's original to our work. Yes. And I don't know. I mean, since I mean, I hadn't thought about this relationship that you just explained. I don't know how to what analogy might exist.
Maybe could I ask a, I think perhaps related question? I don't know if you maybe said this out loud and I missed it, but is there an intuitive reason why one would expect the thing to show up to be the gamma x, like as the thing that makes everything work for mirror symmetry? Like, is there an intuitive reason why one would expect it, or is it just that the calculations are match up?
So there's some like physicsy argument, which you can find in a paper by Galkin and Iritani, and it's kind of, so all right. I think I might have this right. Like if you take the space of loops in your symplectic manifold, and then you look at the space of constant loops, so that's a copy of X, and then you look at the normal bundle to the space of constant loops. So this is the space of maps from like S1 into the tangent bundle of X at each point. And then you can split that into Fourier modes. and decompose it into like the positive Fourier modes and the negative Fourier modes. So the positive Fourier modes, roughly speaking, correspond to tangent vectors from where you're starting at a constant loop and then expanding it into a loop so that the thing that you sweep out is holomorphic. So if you take this positive normal bundle corresponding to things that look like little holomorphic disks, then you can take some kind of Euler class of this bundle. I mean, it's infinite dimensional, so it doesn't make sense to take its Euler class. But you can do some kind of like chain of equalities where at each stage you say, okay, well, imagine this made sense, then I would make this equality and blah, blah, blah. And at the end, you end up with the gamma hat class. And this is supposed to be an explanation. And it's baffling to me, but it's expanded on in this paper by Galkin and Iritani.
Is there anything that the negative nodes correspond to?
I think they give you this. I think they give you this gamma bar class that Chris was just referring to, although I may be remembering that incorrectly. But I think that's.
Thanks.
Sure.
In the paper, did you folks check this for all line bundles or something like that?
Yes, for line bundles restricted from the ambient toric variety.
Mm-hmm.
So yeah, basically, if you have, maybe I can say something a little enlightening about that, which is that, so have a look at the formula, this one. So, you know, by looking at the structure sheaf E, such a grandpa, okay, I keep pointing at the screen with my finger. All right, so here's E. So if we put the structure sheaf E here, then these factors of 2 pi I go away. But if we put some other line bundle, then we would have components of the Chern character in different degrees, and we would end up with some powers of 2 pi I on this right-hand side. And the way they show up on the left-hand side in the period integral is that now, rather than L being the 0 section, it's some non-trivial section. And it looks sort of like the graph of the differential of a piecewise linear function, roughly. And since it's non-trivial in the fiber directions, you get some contribution coming from integrating over the fibers of your SYZ tori. And that gives you these 2 pi I factors. And those computations match up nicely as well. I don't know if that's what you were going to ask about, or if it's helpful. But
yeah, thanks. And that implies the result for all derived category, I guess, just by using generation or something.
yes, I think that's correct.
But is it obvious if you have Floer theoretically isomorphic Lagrangians, for instance? It is a different question, but if you have isomorphic Lagrangians, or Lagrangians related by autoequivalence, like autoequivalence or something like that, is it automatic that the periods match?
Well, then if the two Lagrangians are isomorphic in the Fukaya category, then you expect they're like they have the same Chern character in Hochschild, in cyclic homology. And then that means they have the same, if you apply the open-closed map to the Chern character, those classes in cohomology should be the same. And those classes should be equal to just the homology class of the Lagrangian, or Poincare of the homology class of the Lagrangian. Like they're only counting constant disks by some symmetry argument. So if they're isomorphic objects of the Fukaya category, then they have the same homology class, and in particular, the period integrals are the same.
Okay.
Are there further questions for the speaker before we stop the recording? Okay, well, let's thank the speaker again. Thanks.